Okay. So yeah, I'm gonna talk about some lower bounds on some stuff that you will see. This is based on a couple of joint works with Richard, like Eric Hoff, who's a PhD student in pure math, and Alex May, who's in Perimeter Institute. So I understand that not everyone here is familiar with quantum computation and quantum information in general. So I tried to keep away the technical stuff and I'm trying to show you some connections between some stuff that you may like. So hopefully you'll enjoy it. So first part, I'm going to talk about something called some task called quantum position verification. And then I'm going to show you a couple of proposed protocols for this task. And then I'll give you some lower bounds that we proved for entanglement complexity of this task. Then we'll see an overview of the techniques that we use, and then through that we'll see some connections to communication complexity and then some applications to information-theoretic cryptography. So the first part is somehow mostly related to quantum information, and then we'll see some communication complexity stuff, and at the end some cryptography. So let's start by defining this position verification task. So suppose we have a prover that wants to claim that they're in a certain place at a certain time, and we want to see whether we can have two verifiers v0 and v1. I mean, their goal is to verify this claim. So the picture that you can think of is that we have three separated islands, and the prover claims to be in one of them at some certain time, and then v0 and v1 want to send some signals to this prover and verify this claim. So our focus is on one-dimensional space. So the horizontal line here is the space. The prover is in between, and the black region is the region of space-time that the prover is claiming to be inside it. So the time goes up. So let's see a very simple idea of how to do this. Consider the following scheme. We have a function f that maps 2 n bits to a single bit, and then the first verifier samples x, the second verifier samples y, both n bit strings, and they send this to the prover. And in return, they expect to see f of xy at the right time. So obviously, both all three parties know what the function f is, and you may ask what's the idea here? Well, the idea is that none of the parties can send information faster than the speed of light. So if, for example, in this picture the prover is closer to v1, then it has to wait to receive x from v0. And by the time that it receives x, it has to compute f of x and y, and suppose that it can compute it instantly and has to send f of xy back to v0. But then it takes a longer amount of time than what v0 expects, so it can reject. Okay. So are we done? So I guess the idea here is that if you have one cheating prover, it cannot fool the two verifiers that we have. But what if we have multiple cheating provers? And well, as you can see in this kind of cartoonish example, if you have two provers p0 and p1, where none of them are in that region of space, space-time, they can still implement this protocol. And the way it works is that p0 receives x first, it copies x, takes a copy for itself, sends another copy to p1. P1 does the same thing for input y that it receives from v1, and then they can compute f of x and y disjointly by their own and send the responses to v0 v1. So I guess the bottom line of this is that at least I don't know how to do this classically. So, and as you have seen in the title of the talk, we're going to have some quantums of getting involved. So let's see some very like short. Yeah.
I follow. I think the same about I don't understand why it's fast.
This is not faster. This is like what I'm saying is that they can fool the verifiers V0 and V1, but none of them is actually in that region of space-time. Okay. So yeah, let's see a very brief summary of quantum information. So we have the notion of density matrices, which are n by n positive semi-definite matrices with trace 1. And then if you have a rank 1 density matrix in the form of like U star, where norm of U is 1, then we call this a pure state, and we use this like ket notation for column vectors. A qubit is a pure state in C2, for example, like ket 0 is 1, 0, and ket 1 is 0, 1. And one important thing for us is that there is this no cloning theorem that says, well, if you have like an unknown state, there is no like unitary operation that can copy copy that state in like 2 states. So back to the position verification stuff. The question is, what if we allow quantum restrictions? So the problem, like previously in that like example that we saw, was that the cheating provers were able to copy the like classical inputs X and Y, right? So maybe this like no cloning here is a way to kind of save ourselves from that problem. And there are like 2 like proposed protocols that are essentially based on this property. One of them is the routing position verification scheme, and the other one is like the measuring position verification scheme. And
sorry, yeah, you know that is important. Yeah, I guess I have the same question as Matt. So how do you fool P0 P1 here? Because like
no, P0 and P1 they want to fool the verifiers.
Yeah, so how do they do it?
So P1 is receiving the input y of P1, and then send P1 to P0. So send y to P0.
Right.
And basically okay. And then P0 does the same thing with X. Copy X, like take the copy for results, and it's another copy to P1. And it's not P1 is receiving X from P0. It already has y, so you can compute f of x, y at this point, and then use the closer verifier.
But isn't it the same as if, like, why does that?
If you have only one P1 here,
Yeah,
it has to wait like this amount of time to have to get both inputs, right?
yeah, but don't I have to wait as well the same amount of time? Because I mean,
Well,
now
if you wait this amount of time, you have to like convince both verifiers. So the message is not like perfect at this point.
oh, because you're sending the message back, right? Because you're saying you want to send the message this way, P0 sends the message to P0. But then don't they know that who is sending the message? That was my next question, right? I mean, P1 will know that P1 is sending the message. So like P0 is not going to receive any message back from P1 and say, oh,
it's not receive a message from P0.
Right, but then you're assuming that the verifiers will not distinguish between the provers. That's
So I'm assuming that the P0 and P1 is like P1. I mean, maybe they're both the same person.
So that's that was the assumption on top of that, right? That you don't know who the prover is. Okay, sure.
So I mean, this is sort of indistinguishable from, let's say, a P prime at the intersection point in the middle, or P on the side. Those will look the same.
In the verifier's eyes, they're the same, but in one of them there is a prover in that space time, but in this case there is not.
But in that sense, you're also required, right? So each verifier talks to one prover, right? Because if the verifier talks to both provers, then this is not a problem.
Well, I mean, if the verifier knows there are 2 provers, then it's a problem doesn't really make any sense, right? The problem, like the verifiers are thinking that there is a prover in that like place, and they want to verify that. So if they know that there are like two provers, it's kind of
So the number of, okay, yeah, that's okay. The number of provers is also unknown.
Yeah.
Right. Okay.
Yeah, we're good. Okay, so let's see the definition of these like two protocols that I mentioned here. So we start with the routing scheme. So again, the idea is the same. Like we have like a 2n-bit to 1-bit function f, and then we have like this maximally like entangled quantum state that's shared between like two qubits q and q bar. So again, V0 samples x, V1 samples y, and then like V0 sends x, and one of the two qubits of that like state omega to the prover. So here I'm thinking the q is the qubit that goes to the protocol, and q bar is like for the reference of the verifiers. And then V1 sends y to the prover, and then the idea here is that the prover is computing f of xy. But if f of xy is 0, it has to return the qubit q to V0. And if it's 1, it's returning it to the other verifier, to V1. Okay. And then the verifier that receives the q has to like kind of do a measurement with the reference qubit that they have to make sure that this is in fact the qubit q. So again, like the cartoonish view is that like x and like q are coming from one side, y is coming from the other side. The prover like does this computation and then returns like routes the qubit q to the correct side, depending on the value of yes.
So do both verifiers know exactly why? Because of telling there's something only one of these doing?
Yeah. Yeah, I mean they know, yeah.
They know exactly.
They know, yeah, they know. Yeah. But so the left picture is the honest view. If you have like one single prover, that's what we expect to see. But the non-local view, or like the dishonest view that like kind of involves like two provers, has like a picture like this, where we have like a party on the left side, another party on the right side. They have like this shared resource state, and then they're allowed to exchange one round of messages, and they have to somehow bring Q to the correct side of the computation.
A good question about this picture. So the verifier on the left knows Q, and if it is 0, then the prover has to answer the verifier on the left.
Yes.
But if it's 1, then how does the verifier on the right know that it's 1 and they're supposed to receive an answer? What if
Sorry?
What if the qubit is 1 and the prover does not send anything back? Where the verifier 1 knows that it's not going to get a response.
So the verifier, like the verifiers know which one of them should receive the qubit Q, right? So they know f of xy. If it's 0, the left verifier is expecting to receive Q, and if it's 1, the right verifier is expecting to receive it.
Okay, I see. F of x. Okay. Yeah, makes sense.
I also do again have some sort of time restriction on what's being sent back, or is that the regular? Because in the previous scheme you had a measure.
Yeah, so they have. I mean, they need to receive the qubit Q at the right time. But I'm also kind of like starting to kind of hide it under the rug because it's starting to become irrelevant. I guess what I'm saying is that if in the non-local view they can do these operations with one round of communication kind of like efficiently, then you don't need to worry about time anymore. Okay. Yeah, we also have like this measuring scheme, which is like very similar to the routing scheme. The only difference is that like the prover doesn't need to like send the qubit to the correct side, but they need to do like a measurement on the qubit. But the basis of measurement is determined by the value of the function.
So in the previous slide, you also have to send x X, right? Like the prover has to also send like X to Y and Y to the first group, right? By the time, so they know the value of the function. Because right now, like
let's say verifiers know the value of like X and Y. Like let's say they know like what F.
right, yeah, they have to know.
Yeah,
Okay.
yeah. So yeah, I was saying that the measuring scheme is essentially the same, but the difference is that like the basis of measurement that the prover is doing is determined by the value of the function, and then the output of the measurement is something that the verifiers expect to receive from the prover at the right time. So a quick note is that our focus is on the non-local view, because ideally this is the attack to the position verification scheme, right? So this is the thing that we want to show is hard. So if we can show a lower bound on the resources that the cheating provers need to perform this task, then it's kind of like a security guarantee for the position verification. Okay, now you may ask, like, okay, are we done? Like, is this it? And in particular, are these like protocols secure? And the answer is no, they're not information theoretically secure. I mean, we know some attacks that break the security of these schemes, but these attacks are like very expensive in the sense that they need like the resource, like the shared resource state that the cheating provers need to have is like exponentially large in the input length of the function f. And if you're interested, the idea in those attacks is like some technique called like port-based teleportation. So the main question that's like we're trying to answer is that can we find good lower bounds on like this routing or measuring protocol? So ideally, we want to show that there are some functions that, I mean, the function itself is easy to compute, but like doing this kind of routing non-locally is costly. And there are like some known linear lower bounds on the quantum system size from this work of Blum, Persando, and Spielman. But they mostly consider random functions, and the problem with random functions is that it's not easy to compute even for the honest prover. So our results. Well, the first result is that we show a lower bound on the like Schmidt rank of the shared resource state of the cheating provers, and we also show like a lower bound on the quantum circuit size that they need to apply. And as we will see, like both these lower bounds kind of depend on some like communication complexity measures for this function f. And if you're curious about Schmidt rank, it's basically like a measure of how much entanglement there is in the resource state of the cheating provers. Okay, so let's see some like entanglement lower bounds. Any questions? Okay. So I'm going to make an assumption here, and for this like entanglement lower bounds part, we are only considering like routing protocols that have like perfect correctness on 0 instances. And what I mean by that is that if f of xy is 0, then I'm assuming that the cheating provers will always succeed with quality 1. Okay. So let's see some like notation first. So I assume like perfect correctness on 0 instances, and I'm going to say let like R0 of f be log of the minimal Schmidt rank of the resource state that they need to have if they want to succeed. And well, we want to prove a lower bound on this quantity. And if you ask like what happens with 1 instances, well, we can just like look at the negation of function f. And also let's like R1 of f be the log of minimal Schmidt rank that they need, and let m of f be for the measuring protocol. So R is for routing, M is for measuring. So now let's like consider a routing scenario in the non-local view. So if you remember, the picture was that Alice received some inputs, Bob also received some inputs. They do some like local operations, and then they exchange messages to each other. So after they exchange the messages, let's say M is the set of registers that Alice is currently like holding, and M prime is the set of registers that Bob is holding. And recall that the qubit Q that is like somewhere in the protocol is also like maximally entangled with Q bar. And we want to look at this like density matrix rho of like over Q bar, M, and M prime. So the next thing we do is that we define like a structure function that has like this form. It's like trace of rho over like Q bar and M prime minus like identity tensor rho reduced on M prime squared. And again, M is like the registers that Alice is holding and Bob is like holding M prime. So the idea here is that if f of xy is 0, then it means that they always like, because of the assumption that I made, they always like succeed with probability like 1. So there has to be like no information about this like system Q bar on the Bob side. So that like trace is going to be 0 if and only if like f of xy is 0. And then we can prove like a technical lemma that if you have a routing protocol that has like a resource state with Schmidt rank k, then we can rewrite that function g of xy as sum of like k squared like fi of x times fi prime of y. And the important thing here is that fi doesn't depend on y and fi prime doesn't depend on x. So let's say we kind of write the values of this matrix like gxy this function gxy in a matrix like capital G. And we know that the xy entry of like capital G is 0 if and only if f of xy is 0. And because of the previous technical lemma, we can show that, I mean, if you look at these like fi and fi primes as vectors, then we can like show a bound on the rank of this matrix G, which is like k to the power 4, because we had like k to the power 4 elements in the sum. And well, combining these like two things that I've showed, we can prove the like first main theorem, that if you have like a routing or measuring protocol with like perfect correctness on 0 instances, well, perfect correctness on 0 instances is for routing protocol. For measuring protocol, we're just assuming perfect correctness everywhere. Then the bound we get is that the log of Schmidt rank is bounded from below by 1/4 of log of rank of a matrix G, where like any matrix G that has this property where G of xy is 0 if and only if f of xy is 0. So we can apply this theorem to some like concrete functions. And in particular for equality, we know that this matrix G is non-zero only on the main diagonal. So this this matrix has full rank. So you need at least I mean, you get this like linear lower bound on the log of Schmidt rank. And like similarly, we can like apply the same thing to for the greater than function, because this matrix is also upper triangle, so it's also full rank. So yeah, again, we get like a linear lower bound. Any questions? Yes.
Well, first off, Schmidt rank is very easy. You kind of have very high Schmidt rank and I'm very good at saying all this. You can very close to
No, no, we don't. But why? Well,
you can be arbitrarily close to a product state and still have those right?
but yeah, but if you have like, I guess let's say we kind of like limit the structure of the like the shared resource state to be like just a bunch of APR pairs.
Sure, yeah.
Then you can show that there is like a limit on number of APR pairs that they need to.
Yeah, and another question. Where we are assuming that there's a certain like could be
we're assuming it's pure for now. Yeah.
Is this way possible?
It's let me think.
Potentially it's like a convexity argument that every mixed state is a problem.
If we look at then I have their case further if you want to work case then looking at the error in the I'll listen to that okay then maybe yeah. Sure, yeah.
Okay. Okay, so I mean, for those of you who are like familiar with communication complexity, this like matrix G that I defined is probably looking kind of like familiar-ish. So in communication complexity, we have like this function f that maps like 2n base to 1 bit, and then if we write the values of this function f of xy in the xy entry of that 2 by n times 2 by n, 2 to the n times 2 to the n matrix A, then this is called the communication matrix of f. And well, this shows up a lot in communication complexity literature. And I mean, most of you know that you can get interesting bounds on communication complexity by using properties of this matrix A. And well, just like a brief reminder of what I mean by communication complexity. Well, I mean, Alice holds X, Bob holds Y, they want to compute this function F, and they exchange messages to each other. And the goal is to minimize the amount of communication that they have. And let's look at this definition of non-deterministic quantum communication complexity of function f, which is the minimum number of qubits that Alice and Bob need to exchange, such that like both of them output 1 with probability that it's like strictly greater than 0 when f of xy is 1. And both of them should output 0 with probability exactly 1 when f of xy is 0. So as an example, if for example you consider disjointness problem, like the parties can just sample a random element and like send it in, like one of the parties can sample a random element of its set and send like the index of it to the other party. And if there is an intersection, there's like a positive, like the probability of like sampling something from the intersection is strictly greater than 0. And if it's not, it's always 0.
Why is this called non-deterministic and not what's better?
Well, to be honest, I don't know. You can ask Ronald DeWolf, who like introduced this in 2003.
And the success probability should be arbitrarily like potentially very high.
So what do we know about this quantity? Well, the Wolf showed that if you have a matrix A, where A of xy is non-zero, one of xy is 1, like let's call this a like non-deterministic computation complexity matrix for F, and let's like non-deterministic rank of this function F be the minimal rank of any such matrix like A. And then he showed that this like quantum non-deterministic communication complexity is like exactly equal to like log of non-deterministic rank plus 1. And for us, I mean, we can get this like immediate corollary that the log of Schmidt rank is bounded from below by this QNPCC of F. And we can say the same thing for one instances, but this time it's like co-QNPCC of F, and also for measuring protocol, we get the same bound. And just like one like small comment is that the matrices that we had like in the proof, the entries of the matrix are like reals, but the ones that we have in like the Wolf's work can have like complex value entries. So there's like a small like difference in the definitions of these two matrices. Any questions? Okay, if not, then I'm gonna go to the next result, which is some like lower bounds on the gates that the parties have to apply. And we need another measure in communication complexity, which is called like simultaneous message passing. And here, suppose we have like 3 parties, Alice, Bob, and Carol. And Alice sends a message to Carol, Bob also sends a message to Carol, and then Carol is supposed to compute f of xy. So here Alice and Bob don't like talk to each other. And let S and P of F be the minimum number of bits that they need to communicate. And let S and P star of F also be the minimum number of bits that they need to communicate, but they also have like shared entanglements between them, Alice and Bob. So it's like here's like a straightforward lower bound for SMP star. It's bounded from below by quantum one-way communication complexity. Or because you can just think of Carol being as one of the parties A and like Alice and Bob, and then the other party is sending the message to Carol. I mean, here I'm assuming that Alice sends like a classical message to Bob, but they also like share entanglements. So to show like a reduction from that like position verification stuff to SMP, we need this lemma, which I'm setting from this work of PCS, where if we have like this like mid-round density matrix that I talked about before, and let's like S0 be the set of such rows such that Alice can somehow recover the like qubit Q on her side, and S1 be the set of density matrices rows such that Bob can recover the qubit Q on his side. And I'm saying recovering with high probability here because we don't need the perfectness assumption for this part. Then if the success probability is large enough, if they're small, then these sets like basically don't intersect. So intuitively, this means that like after exchanging messages, they should already have like kind of committed to the qubit Q being on the left or the right side. So after they exchange the messages, it's kind of everything afterwards is like just some like post-processing. And let's go back and consider a circuit that Alice applies to her system before exchanging the messages. Well, the main idea is that if the circuit is small, and if also like the circuit that Bob is applying is small, then we can get an efficient like SMP star protocol for this function f. How? Well, I mean, if the circuit is small, then she can send like a description of the circuit to Carol. And Bob can also send a description of the circuit to Carol. And Carol is basically like simulating the operations of the routing protocol, given like these like description of circuits, and sees whether like the qubit is on the left or on the right side, and then decides whether f of xy is 0 or 1 based on that. So if Q is the quantum system size of Alice and Bob, and let's say they're used like a universal gate set of size 4, for each gate they need like two Q many bits to specify like the inputs and the gate that they're applying. And for each measurement that they apply, they also need like 1 bit, like to show what's the output of the measurement, and log Q many bits to specify where they're applying the measurements. So we can get the following theorem that if they have like, if there is like a cheating protocol that succeeds with high probability and uses like CG many gates and CM many like single qubit measurements, then we can bound like this CG plus CM from below by this SMP star times some by Q. And here I'm assuming that I mean, we don't need perfect correctness here. I'm just assuming that they succeed with high probability. And well, we have this work from 2002 by Nayak and Salzman that they show a lower bound on quantum one-way communication complexity of inner product function, and they show that this is like linear. So this immediately gives us like a linear lower bound for inner product in the in terms of gates and measurements. Yes. Yeah. There is a like this is. I think they improved the constants and stuff. Yeah. Yeah, I just stated the most recent result, but I simplified it like to omega. Yeah. So let me just like quickly like compare this result to what of BCS. So the difference is that they I mean they show like a similar reduction but to SMP, but the difference is that they look at the like the purified view of the operations of Alice and Bob. They look at the unitary operations. So in a sense, they're also like kind of including the classical parts of the operations in the lower bound, but ideally we want to like kind of separate the quantum and classical operations to get a better lower bound. And yeah, in the last part, I'm just going to say some stuff about like some applications in information-theoretic cryptography. And in particular, I'm going to define this like protocol called conditional disclosure of secrets, CDS. So we have like 3 parties here, Alice, Bob, and a referee. There is again a function f involved. Alice holds input x, Bob holds y, and they also have like a secret s. And they send these like messages MA and MB to referee. Referee also knows x and y. They also have like some like shared randomness between them. And the goal is that if and only if f of xy is 1, then the referee is learning the secret s. Okay, so if f of xy is 0, the referee should like learn no information about s, and if it's 1, it should know what s is. And think of s as being just like 1 bit. So this like notion has been extended to the quantum case, I guess. And well, this is, I mean, we don't define this problem, but I should change that in the slide. But it's been defined that like CDQS as the problem where the secret is a quantum state Q. And they also have like shared entanglement now instead of shared randomness. And they call it like CDQS. So here the thing that we're interested in is like, what's the minimum number of shared bits that Alice and Bob need to perform this task like with bounded error? And we call this like it's been called like CDS of this complexity for a function f. And there's also like a perfect privacy case of CDS, where by that I mean if f of xy is 0, then the referee learns no information like about the secret S with relative 1. And also let CDQS be like the minimum number of like shared qubits that they need to perform this operation. So there is this theorem by this set of people. I don't remember all the names, but I remember Berman, May, Spielman. But yeah, ask me later if you're interested. But they show that this like CDQS complexity is basically like equal to the complexity of doing the routing protocol with bounded error. And they also show that CDS, like CDQS is at most equal to CDS. And it's kind of not hard to see if you're familiar with like quantum one-time pad, because what you can do is that you can just apply one-time pad and do CDS on the keys of one-time pad. And then like a corollary of like their result and our result is that like the perfectly private CDS is bounded from below by this Q and PCC. I know that this is like for the classical perfect private CDS. There's no like quantum involved. So for perfectly correct CDS, we have like this bound from this work of Applebaum and Vasudevan from 2019 that is bounded from below by co-n PCC of F. And what we show is that like perfectly private case is bounded from below by Q and P. So it's interesting because like the bound that we show is like a, I don't know, like a quantum communication complexity measure for a classical task. Okay, that's mostly it. Let me just summarize quickly that I guess we proved the first like non-trivial lower bound on the entanglement complexity of attacks on this like routing and measuring schemes. And well, unfortunately, the caveat is that the technique only applies when the scheme is like perfectly correct on one side. But we also show some lower bounds on the like circuit complexity of these attacks. This one is like robust, fortunately. And this kind of has some applications in bounding the randomness complexity of this conditional exposure of secret. And for open problems, let me mention that, well, I guess the first obvious like open problem is to prove a robust lower bound that doesn't need this assumption about perfect correctness. And I guess like it would be interesting to see like whether there's like a direct reduction from like this routing to quantum non-deterministic communication complexity, because it looks like the techniques like are similar, but at least I couldn't think of a direct connection between the two. Another question is that can we get better lower bounds for CDS using these techniques, or maybe other techniques? Because, well, to some extent, it feels like if you're like reducing to communication complexity, you can't expect to get anything better than linear unless you do something like super non-trivial. So if you want to get better lower bounds, maybe there are some like you need some like new ideas to think about. And yeah, thank you very much.